Welcome back. Today we'll be doing 3.5 part 2, compound inequalities. And really this is just going to combine our previous work in 3.5 with the single inequalities with our work in set theory on unions and intersections. So there's some ideas that are coming back to us. So we'll start with some ands. So 6x is strictly greater than 30 and 8 is greater than or equal to 4x. So we'll start by just solving these individually. So the first one, I'm dividing both sides, but it's by a positive, so my inequality symbol stays pointed the same direction. And 1 times x will simplify down to x, so x is greater than 5. Remember, we can also use this symbol for the and, or you can write the word and, but you do need at least one of those. Our next one, we would divide both sides by positive 4. As long as I'm dividing by a positive, inequality stays put. And yes, I'm still quarantined with my cute little 9-month-old. All right, so far just 2 separate problems that are similar to what we did in 3.5 part 1. The only difference is now instead of drawing 1 number line, we're going to draw 3 number lines, 1 for each individually and then 1 for the intersection in this case. So x is strictly greater than 5, so the key points are 2 and 5. And we'll just put a couple points either side. So x is strictly greater than 5. I'm not allowed to use 5. And trying out a test point, 8 is greater than 5 works. 1 is greater than 5 doesn't work. Dots go on the side that works. 6, 7, 8, 9, and forever this way. Next we'll do the 2 is greater than or equal to x. So I'll put up the same sketch we had before. This time the key point is at 2. Trying 1 on each side. 2 is greater than or equal to 8 does not work. 2 is greater than or equal to 0 does work. Dots go on the side that does work. This time, because of the or equals, we do get to keep the 2. So the 2, the 1, the 0, and forever in this direction. So next, we look for the intersection of these two. Intersection, the ands, it has to be in both sets in order to keep it. So notice the stuff over here was just in graph 2. The stuff over here was just in graph number 1. This one, my number line actually ends up being blank. There's nothing that works for both. So my solution would be an empty set. However, if I change one thing about that, so this one was our intersection graph, I'll do the what if in red here. If this instead were an or, everything was the same, but it were an or, which means we would have a union symbol. All the rest of this work would look the same, but let me do a new graph for our union instead. And we'll go ahead and pretend that I was drawing those nice and evenly spaced. If we have a union instead of an intersection, union, if it's in one or the other or both, we get to keep it. So because of graph number 1, I'm going to keep the 6, the 7, 8, 9, and forever in that direction. Because of graph number 2, I'll keep the 2, the 1, the 0, and -1, -2, -3 forever in that direction. So which one it is depends on if it is a union or an intersection as far as what our set would look like. This time our set has really 2 parts. So the first one, we're coming from the left, -infinity, and then we list out 4 points, so -1, 0, 1, and 2. Then we have our union symbol, and just show where it picks up. So 6, 7, 8, 9, and forever in that direction with 4 points. And remember, these are braces, not parentheses. And yes, she is learning to, well, not talk yet, but certainly make some noise. All right, so next up, let's see, we'll just start a fresh page. We'll need the room. So we'll do an x minus 5 is strictly greater than -2. Again, we'll start with the and we'll look at what it would look like as an or as well. 2x minus 7 is strictly less than 9. So solving these, my first one, I would add 5 to both sides of the inequality. Adding, your inequality symbol will never move. So x is strictly greater than 3. And our second one, we'll add 7 to both sides of the inequality. Addition never moves your inequality. We'll divide both sides, but it's by a positive, so as long as we're dividing by a positive, the inequality symbol won't move. So x is greater than 3, intersection with x is less than 8. So then we will start our drawings. I want to be able to fit the 3 in there with a couple on either side, 8 in there with a couple on either side. So maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 would be fine. Oh, we went up 12. Okay, that is fine. All right, so our first one is going to be the sketch for x is strictly greater than 3. So here's the 3, sort of cuts our graph in half, and we just try a test point. 11 is greater than 3 works, 1 is greater than 3 doesn't work. So we want the side with the 11. We are not allowed to use the 3, we had strict inequality there, so we'll start at the 4. And we go forever that way. Next, we'll sketch the x is strictly less than 8. And again, a little imagination, we can picture those correctly spaced. All right, 4 is less than 8 works. 10 is less than 8 does not work. Dots on the side that work. Strict inequality on this as well, so I'm not allowed to use the 8. And my ellipsis goes up and to the left this time. And then what we use, we'll start with the intersection, and then we'll look at a union next. Okay, so intersection, we want only things that are in both lists. So 4 is listed both times, so is 5, so is 6, so is 7. 8 is not listed both times, so our solution set for the intersection would just be those 4 elements, 4, 5, 6, and 7. This time we'll do the union in blue. If they said or, it would have been a union. All this other work would have been the same. First 2 graphs would have looked the same. Now we'll graph our union if we had a union instead. So union, if it's in one or the other or both, we get to keep it. So because of graph number 1, I'll keep 4, 5, 6, 7, 8, and forever that way, because it was in at least one of them. Because of graph number 2, I'm also going to keep 3, 2, 1, and forever that way. So in this case, our solution is I, the set of integers. Every single integer we got to keep if it were a union instead of an intersection. So just watch out for which one are they asking, and or or. All right, one more and then we'll go to the two-part ands. Let's try a negative 3x plus 2 is strictly greater than 8. Again, we'll start with the and. It depends on which one they ask you for. They're typically not going to ask you to do both of them in one problem. I just want you to see both times how it's done. Let's see, our next one, 18 is strictly greater than 2x plus 10. So our first one, I will subtract 2 on both sides of the inequality. So negative 3x is strictly greater than 6. Then I'll divide both sides by negative 3. And I hear the alarm bells clanging. Divide both sides by a negative, you have to flip your inequality. So x is strictly less than negative 2. And we will intersection that with what we get from our next one. So the next one, I would subtract 10 on both sides. Add or subtract all you want from an inequality. Inequality symbol stays put. Then we'll divide both sides by a positive 2. Dividing by a positive, the inequality will not move. Okay. So our sketches. So let's do maybe negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so picture that with the rest of them filled in. Our first point that we're interested in, we'll do the ands in red this time again. So this one will be for the x is strictly less than negative 2. Here's the negative 2. 8 is less than negative 2 does not work. Negative 5 is less than negative 2 does work. So we want the side with the negative 5. And forever in this direction. And again, picture the rest of the number line filled out. So next one, this is for 4 is strictly greater than x. So our dividing line is at the 4. 4 is greater than negative 2 is true. 4 is greater than 8 is false. Dots on the true side. So we will keep the 3, the 2, the 1, 0, negative 1, negative 2, negative 3, negative 4, negative 5, and so on in this direction. So then what we do next just depends on which one they asked us for. This one they asked us for the and. So the intersection graph. Intersection, we only want things that were shaded twice. Over here, none of this got shaded at all. In this region, only shaded once. Over here, starting at the negative 3. That was shaded both times. We'll hang on to that. -4 was shaded both times. -5 shaded both times, and forever this way for our intersection. So our solution set for that, we are coming from -infinity, so -6, -5, -4, -3. We did not get to keep the -2 because of the strict inequality. It was not on our first graph. If instead they had asked us the OR, the rest of this in black would look the same. First two graphs would look the same. Our final answer would look different. So this will be for the OR. Okay. If it is a union, if it's in one or the other or both, I get to keep it. So all of this back here that we shaded twice, we'll definitely keep that stuff. And that's through to the -3. But because now we're going for a union, not an intersection, I do get to keep all of these guys because of graph number 2. So here's the -2, -1, 0, 1, 2, 3, and 4 was not shaded either time, so we did not keep the 4. So if the question was an OR problem rather than an AND problem, one number set only, we're still coming in from the left-hand side. Only this time we get to go all the way up to 3, so up to 0, 1, 2, and 3 on the integers. So then our other new piece in this is the double inequality with an AND. If we have the same thing left and right, so for example, -18 is less than x plus 7, and x plus 7 is less than -15, then what we can do is shorten that. Because we have the same argument and the inequality is facing the right way, this is sometimes then shortened to -18 is strictly less than x plus 7, which is strictly less than -15. So now we have an inequality with 3 pieces rather than 2, but the ideas to solving it are the same. If I were to show you this inequality and say solve this, you would hopefully say I would subtract 7 from both sides of that. If I showed you this inequality and said solve this, hopefully you would say I would subtract 7 from both sides of that on the next step. That's exactly what we'll do, only we have 3 pieces instead of 2 pieces. So -18 minus 7 less than x plus 7 minus 7 less than -15 minus 7. And we can add or subtract all we want. These inequality symbols don't move. So -25 is less than x plus 0 turns into an x, which is less than -22. When this is the case, nice thing is we only need now one graph, similar to what we did in part 1 of this section. So again, I'll just go a few on either end of the numbers, so -28, -27, and so on. Okay, so that is sufficient to get it at least started. This time I do not get to keep the endpoints. X has to be between the two of them, not on either one of them. No or equals under either one. So I'm not allowed to use the -25, but -24 works. It's bigger than -25 and smaller than -22. -23 will also work just fine. It's bigger than -25, but smaller than -22. However, that's as far as we can go. -22 is not less than itself. If they had the or equals, then we could keep that. So pretty small set this time. We can keep negative 24, we can keep negative 23, but nothing else. Of course, it's not always necessarily a one-step. It may be a two-step inequality. So if we have maybe negative 5, strictly less than 3x plus 2, which is less than or equal to a positive 5. If this were an equation, we'd subtract 2 on both sides. If this were an equation, we'd subtract 2 on both sides. So we'll do that with this compound inequality, negative 5 minus 2. Less than 3x plus 2 minus 2, less than or equal to 5 minus 2. So negative 7 is strictly less than 3x plus 0 turns into 3x, which is less than or equal to 3. Then we'll divide by 3. And you should see that whichever one you look at. So negative 7 divided by positive 3. Dividing by a positive, the inequality symbol stays as is. So 3 would go into 7 twice with 1 left over. So negative 2 1/3 is strictly less than x, which is less than or equal to positive 1. Remember, in this chapter, we are working with integers unless otherwise specified. So I will not get to keep the negative 2 1/3, but I can get close to it. So negative 2 1/3. Remember, that is a little to the left of where negative 2 is, not to the right of it. Remember how we're counting with the negatives. 0 to negative 1 to negative 2, then over to negative 3. Negative 2 and a little bit further left. So we will get to keep that negative 2 since it is bigger than negative 2 1/3 and it's less than or equal to 1. Negative 1 fits the bill, 0 does as well. This time we do get to use that endpoint. We had an or equals on the 1. So then our solution set, negative 2, negative 1, 0, and 1 only. So that should give you enough information to finish out section 3.5. That one was a little bit on the shorter side. And if you have any questions, make sure to get in touch with me. Otherwise, I will see you for the next video on absolute value inequalities. So homework finish 3.5, the ands and the ors.